All right, let's dive right into a choice that every backend developer has to make, whether they realize it or not: synchronous versus asynchronous design. Now, I know it sounds a little academic, but trust me, getting this wrong can absolutely cripple your system's performance.
And I'm not talking about some theoretical problem. Look at this. This is from a real-world system. A simple architectural change led to a 54 times performance boost. Yeah, you heard that right. A request that took almost a full second dropped to just 15 milliseconds. This isn't about buying faster servers. It's about choosing a smarter architecture. And a gap this huge, it's usually a symptom of a much, much deeper problem.
So, here's the thing you've got to understand. The biggest performance killer in most apps today isn't how complicated your code is. It's I/O, input-output. It's all that dead time your code spends just waiting for a database, waiting for a file to load, waiting for another API to get back to it. This waiting, it's the unseen enemy of performance. And that brings us to this concept: blocking I/O. In this model, when your code makes a request, say to a database, the thread running that code literally just stops. It's blocked. It can't do any other useful work until that database finally responds. Think of it like a factory worker who has to stand there, completely idle, just waiting for a part to arrive on the conveyor belt. This slide really lays it all out. On the left, with blocking I/O, that thread is basically asleep on the job. Those are precious CPU cycles just getting thrown away. But on the right, with non-blocking I/O, the thread makes the request and is immediately free to go do something else. No wasted time, no wasted cycles.
Let's just walk through it, step by step. A request comes in. A thread gets assigned to handle it. The thread makes a call out to a database or an API. And then we hit step 4, wait. And this is the killer. This step could last a few milliseconds, or it could last for seconds. And for that entire time, that thread is totally useless. It's only after the waiting is finally over that it can process the response. This wait state is exactly where systems grind to a halt when they get busy.
So how have we traditionally dealt with this? Well, the most common answer is the synchronous thread pool. The best analogy is a restaurant with a fixed number of waiters. Each waiter can only take care of one table at a time. If all your waiters are busy, either taking an order or just waiting for the kitchen, any new customers have to just line up at the door and wait.
And this right here shows one of the biggest problems with that whole model: the cost. Every single one of those threads eats up resources. In Java, a typical thread needs about a megabyte of memory for its stack. So if you want to handle 1,000 users at the same time, you've just used up a whole gigabyte of RAM, just for threads that are mostly sitting around doing nothing. That does not scale well at all.
And it's not just about memory either. As this quote points out, there's a huge CPU cost too. The operating system has to constantly swap these threads in and out of the CPU. It's a process called context switching. Every switch has a little bit of overhead, and when you have thousands of threads, your system can end up spending more time just managing the threads than it does doing any real work.
Now let's look at how this plays out with a tool that millions of Java developers use: the thread pool executor. Its logic is famously and frustratingly counterintuitive. You'd think it would add new threads until it hits its maximum, then start putting tasks in a queue. But nope. It fills up its core threads first. Then it fills up the entire queue. And only after the queue is totally full does it start adding more threads. It's a classic trap that causes requests to sit and wait in a line, even when the system has plenty of capacity to handle them.
Okay, so that brings us to the modern alternative, the one made famous by platforms like Node.js. This is the asynchronous event loop. So instead of our army of regular waiters, imagine you have one single super fast waiter. They zip over to a table, take an order, hand it to the kitchen, and while that food is cooking, they're immediately off to another table to take their order. They are never, ever idle. The magic behind this whole thing is the event loop. It's a really simple but incredibly powerful idea. It usually runs on a single thread. And what it does is, it fires off an I/O operation, and instead of waiting, it just attaches a little note that says, "Hey, call me back when you're done." Then it moves on to the next thing. When that database call or file read is finished, the system lets the event loop know, and it runs that call me back function. This is how a single thread can juggle thousands of concurrent connections without breaking a sweat.
So which one's better? Well, like everything in engineering, it's a trade-off. The synchronous thread pool model is way simpler to think about. The code reads from top to bottom, it's easier to debug, but it just hits a performance wall when you have a lot of I/O. The async model, on the other hand, is ridiculously efficient for those I/O heavy jobs. But it can make your code harder to follow. You might have heard the term callback hell.
Now, to be fair, things like async await in modern languages have made this a lot better.
And this right here is maybe the most important counterpoint. Performance isn't the only thing that matters. As this developer points out, you have to think about the human cost. Is your team ready to handle the complexity of async code? Do all the libraries you depend on even support it? Choosing a super performant architecture that nobody on your team can maintain, well, that's just a recipe for disaster.
Okay, so now for some fun. Let's look at what happens when you take these ideas and push them to their absolute logical extreme. We're going to peek inside the LMAX disruptor. It's a concurrency framework that came out of the world of high-frequency trading, where literally every single nanosecond counts.
The team at LMAX discovered something that just blew their minds. At the scale they were working at, the standard way of passing work between threads, using a queue, was itself a massive performance bottleneck. The overhead from just managing the queue was as slow as writing data to a physical hard drive. I mean, that's just insane.
So their solution was this brilliant piece of engineering called a ring buffer. It's a perfect example of what's called mechanical sympathy, designing your software to play nice with how the hardware actually works. It uses clever memory tricks and low-level CPU instructions so that multiple threads can coordinate their work without using slow, clunky locks. This is the secret sauce behind the disruptor's unbelievable speed.
And just look at these results. They're absolutely staggering. The average latency drops from nearly 33,000 nanoseconds with a standard Java queue, all the way down to 52 nanoseconds with a disruptor. But the number that really blows my mind is the 99th percentile. It goes from over 2 million nanoseconds, that's 2 full milliseconds, down to just 128 nanoseconds. That is the kind of difference that makes or breaks a high-frequency trading firm.
Okay, so we've gone from the basics of blocking I/O all the way to the cutting edge with the LMAX disruptor. So how do we bring this all back and make the right choice for our own projects?
Well, it really just comes down to asking the right questions. What kind of work is your app really doing? Is it mostly crunching numbers, or is it mostly waiting for the network? How many concurrent users do you actually need to support? And maybe most importantly, what's your team's comfort level with these different ways of thinking? Being honest about these will point you in the right direction. And if you just want a cheat sheet, well, here it is. If your app has moderate traffic and you value code that's simple and easy to debug, the classic synchronous thread pool is a totally fine choice. But if you're building something that needs to handle thousands of connections at once and it's mostly I/O bound, the raw efficiency of an asynchronous event loop is almost impossible to beat. And that brings us to one final exciting thought. There are new innovations on the horizon, like Project Loom's virtual threads in Java, that promise to give us the best of both worlds, the simple, easy-to-read synchronous code that we love, but with the incredible scalability of the async model underneath. Could this be the future that finally ends this whole debate? Well, that's a question we'll all be watching very closely.